This is part 3 of this DC link capacitor calculation stuff. So part 1 was about how to determine the switching states of a three-phase inverter based on some parameters like modulation index and the power factor. I guess the power factor isn't really or I guess yeah, the power factor determines the voltage phase shift relative to the current. So yeah, so we're basically taking the modulation index and the power factor as parameters, and I guess the phase current and all these other things in order to determine the switching states and the current through the switches in each of these states, such that we can determine the DC link current. And then from the DC link current, we can say that the AC component of the DC link current is the current through the DC link capacitor, and then we can determine the DC link voltage ripple based on I is equal to C dV dt. So that's basically what the last two parts covered, and scrolling through this long script that calculates all of these discrete waveforms. And in part 3, I'm going to be talking about how I added these parameters at the beginning that basically calculate what the power factor and the modulation index are for a given motor from certain motor parameters. So yeah, script for plotting DC link capacitor current and voltage from parameters, this time with non-salient motor parameter calcs. So yeah, this is basically, this calculation is for a non-salient pole motor. Salient pole motor basically meaning the inductance of the motor actually changes based on the rotor position. So that would affect our calculation of the power factor and modulation index if there was saliency of the poles, but we're assuming no saliency, which makes all the controls easier and everything. So it's typical. So here's the motor parameters. We have the series resistance of the phase. We have the series inductance of the phase. We have the number of poles of the motor. We have the total flux linkage per phase. So if you imagine a motor, it has permanent magnets on the rotor. There's going to be flux field lines, and those field lines are going to be going through each of the coils of the stator, and all of the flux that's going through the coils of one phase, that's the total flux linkage per phase. And then from that, we can calculate the torque constant of the machine, or if you just get the torque constant from, I don't know, a data sheet maybe, if you have a data sheet for a motor, or you just calculate the torque constant analytically or empirically. Like you can calculate the torque constant in like ANSYS electromagnetics. Maybe I'll make a video on that, just like you basically just simulate the motor, and then the torque constant is basically just going to give you how much torque you get out of the motor for a given phase current, or I guess this is for a given IQ current. And then this is like a back EMF constant, which isn't necessarily like a thing, but it's just sort of, this constant is going to give us, based on the rotational speed of the motor in radians per second, what is the back EMF voltage of one phase going to be due to the speed of the motor. And then we're going to input parameters. So we're saying right now the torque of our motor is going to be 200 Newton meters. So then we're going to calculate, okay, what phase current do we need for a torque of 200 Newton meters? We divide by the torque constant, and we get whatever phase current we need. And in this case, the phase current is equal to the Q-axis current, just because we are going to be, there's going to be no misalignment between the Q-axis and the phase, I guess, assuming that we're not doing any sort of field weakening. And then the RPM of the motor, so we're saying 6,000 RPM motor right now is our operating point. So then the fundamental frequency, the electrical frequency, fundamental frequency, is going to be the RPM times the number of poles, not pole pairs, divided by 120. If you use pole pairs, it's just RPM times pole pairs divided by 60. It's just algebra, I guess. And then W, which is actually supposed to be omega, is going to be the rotational speed of the motor in radians per second. So the RPM times 2 pi over 60 is going to be converting that to radians per second. So then now we can calculate the phase voltage in the using complex numbers. So we're going to end up getting a vector relative to the vector of the phase current. So we're going to say the series resistance times the phase current is going to give us a vector. Maybe I'll draw in MS Paint. This would be fun. Okay. So we have so we're going to have a phase current, which is the same as the quadrature current right now, but let's just write I phase, and then I phase is pointing in this direction, and then for the voltage, let's just make it blue or indigo, or whatever color. So the phase voltage is going to be the sum of all of these vectors. So the resistance times the phase current. So the resistance is tiny, so we're going to add all these vectors tip to tail. So say we have this tiny R series times I phase, and then we're going to have this other component that is going to be J times omega times this should be omega. This should be omega fundamental, omega electrical actually. I'm going to write a new variable here. Whoops. Okay, omega naught is equal to fundamental frequency times 2 times pi. This is, I mean, why don't I just write, let's just do times 2 times pi times fundamental frequency, electrical fundamental frequency. Come on, man. Alright, let's start running this. Ooh, that ruined the power factor, huh? But I guess that makes sense. So, yeah, so then we have J times 2 times pi times fundamental times LS times I phase. So that basically puts us, this is real, and this is imaginary. So J. So then from this J times 2 pi times fundamental times L series times I phase, we end up getting a vector in this direction. And then from the back EMF of the motor, the back EMF of the motor is always going to be in phase with the phase current as long as the phase current is in line with the Q-axis current. And we're not doing field weakening. So then we get another vector like this. So then the overall vector for the voltage ends up being all of these added tip to tail. So then, whoops, don't want to do that. So then we end up getting this phase shift between the phase voltage and the phase current. And then from that, so we have this complex vector for V phase. So then V peak, the peak value of this phase voltage is going to be the magnitude of the phase voltage. And then the angle relative to the current is going to be the angle of this vector relative to the phase current. So we get phi. So then the power factor is going to be cosine of phi. Don't save. I guess maybe I should have saved. That's not even a good drawing. So then here I'm just displaying what the power factor of the motor is, and then based on the DC link voltage, we can calculate what modulation index we need in order to achieve the peak phase voltage that we got from the phase voltage that we calculated. So V peak is equal to the absolute value of V phase. So then with sine PWM, the modulation index is going to be equal to 2 times the peak phase voltage divided by the DC link voltage. And for third harmonic injection, it's going to be square root of 3 times the peak phase voltage divided by VDC. So this is one of the tricks of third harmonic injection / space vector PWM, where you can get a little bit more phase voltage out of the same DC link voltage. So then here I'm writing down the capacitance of the DC link, and then this is just like, you can just put in your own modulation index if you want. So then here the switching frequency, this is all stuff now from the first video. We have the switching frequency, switching period, the number of DC link caps, the ESR of one DC link cap, and then the ESR of all the DC link caps in parallel. So then you get 2 periods of fundamental frequency, number of discrete samples that in our array, time step of each sample. And we're generating the 3-phase currents. So you can see we wanted 200 Newton meters. So then based on the torque constant, we calculate that we need a phase current. Where is it? Should probably display it in the window. Where's I phase? Am I blind? There it is. We need 476 amps of phase current in order to achieve 200 Newton meters. And then we need 0.63 modulation index to achieve a phase voltage that can support 600 RPM, and only 0.546 modulation index for third harmonic injection to support 600 RPM because of the back EMF. So here we have our phase currents, and then here we're calculating the switch states based on the modulation index and the switching frequency, similar to the first video. And then we have the voltage vector states, and then we have the pole voltages unfiltered, and here you can see this is the pole voltage once it's been filtered for sine PWM. This is the pole voltage for the phase current, or for the phase voltage, or the pole voltage using third harmonic injection. And again, in the last video, I sort of touched on this point, how third harmonic injection, you're basically adding this this component to the neutral of your Y-connected load, and then once you subtract that out from each phase, so you're basically adding this third harmonic to all of the phase voltages, and you can see in the Y-connected load the voltage between the pole and the neutral is going to be the pole minus the neutral. So when you add the same third harmonic to all of the phases or all of the poles, that makes it so that the neutral voltage is actually having the fundamental of the third harmonic. So then when you subtract the pole, which has the fundamental plus the third harmonic minus the neutral, which is just the third harmonic, you end up getting a pole voltage that is basically the value of the fundamental within your pole voltage. And like I said, this trick allows you to increase your peak-to-peak phase voltage beyond you're basically increasing your peak-to-peak pole voltage beyond what your DC link actually is, whereas with sine PWM you max out at the DC link. So yeah, we're getting the switch states. Like we said in previous videos, we see sine PWM, third harmonic injection PWM. We see a phase shift because of the power factor. Then we have this DC link voltage. You can see it's slightly going negative sometimes because the power factor isn't 1. So then we have an average DC current of 189 amps. And then we're subtracting out that average current to get the capacitor current. Again, like in the last video, we talked about all the DC link stuff, or DC link cap stuff. So now we have the sine PWM cap. IRMS is 200 amps. So then with the ESR we calculated, we get 40 watts of loss in these DC link caps. And now we can see the voltage ripple due to the parameters we input with sine PWM and third harmonic injection PWM. You can see the third harmonic injection PWM improves the voltage ripple. And then here we can see the efficiency. This last calculation is basically it's only really taking into account the resistive loss in the stator windings in the phase. So the DC current, the DC power in is just the DC average we calculated from the instantaneous current we got multiplied by the DC voltage, and then the AC power out is just the power factor times 3 times RMS phase times RMS voltage, and we get we get exactly the same number as the DC power in, because obviously in this model I could account for the losses in the DC link caps, but honestly it's pretty marginal in this example. And then the mechanical power out, you can see it's obviously lower. The mechanical power out is equal to the torque times the speed in Newton meters and radians per second. And then this efficiency is really only including the resistive losses in the motor. So the efficiency is just the mechanical out divided by the electrical power in. And here I calculated the winding resistance loss. It might not be exactly correct. We have like 1.3 or like 13 kilowatts. These are like 10 kilowatts apart from each other. So I mean it's like it's pretty much just the resistive losses that we're accounting for in this model. And basically, yeah, like I said, the DC power in is the same as the AC power out because we're not accounting for any of the losses in the inverter in this model. But I think I'll make a part 4 to this actually. on this script. Sneak peek. I don't want to go into too much detail right now. But this is just going through all the losses in the inverter. I guess in the inverter switches. And based on the parameters of your inverter switches, you can calculate what the loss in the inverter is for the given parameters that we have in here as well. So I'll probably make a part 4 video, maybe not immediately. I'll probably upload these first 3 parts all at the same time. I just spread them out because they were really long videos and I just end up rambling because I don't know how to explain this very well in simple terms. But yeah, I guess recap of everything. If you want to calculate the switching states of your inverter switches and the power factor of your load and the modulation index that you need to apply to achieve the load you want, or the current you want in your load, then you need to basically you just need to input whatever modulation index or power factor you want, and then you can calculate all those switching states and the currents and the switch voltages and the DC link currents and the DC link cap currents and all that. But if you have a motor as a load, you can input all of these characteristics of your motor and calculate what power factor and modulation index you want. Maybe I'll just plug in something else. Let's see, like 12,000 RPM, 300 Newton meters. Let's see what we get. Terrible power factor. Oh, okay, so actually, wait, this is a good point I forgot to bring up. So see, now you can see that the RPM, once it's at 12,000, now the modulation index is actually over 1. So at this point, we can't actually supply enough voltage to the phase in order to allow it to rotate at 12,000 RPM. I think that's a concept I've covered in a previous video that I did for some lectures at Cal Poly using ANSYS, basically talking about how to calculate the torque speed curve of a motor using ANSYS. But that's basically called the base speed, and the base speed is once you hit the point in the rotation of the motor. Let's just search it up. Permanent magnet synchronous motor torque speed curve. So yeah, I covered this previous video. You can see the torque speed curve. This is at constant current. You end up hitting this base speed, and the base speed is basically the point where if you spin the motor any faster than this, you will not have enough voltage from your DC supply in order to account for the back EMF of the motor. So since I input an RPM that is above the base speed, the modulation index has to go above 1, which, I mean, you can modulate above 1, but this won't actually allow you to rotate faster than 12,000 RPM. So let's change it to like 10,000 and see what we get. Let's just do like 100 Newton meters. So now it loaded. I'm totally just rambling in this last video, sorry. What was I saying? Oh yeah, so we changed the torque and speed parameters. We get a new power factor and new modulation index. You can see third harmonic injection. The modulation index is lower because of that third harmonic trick. We basically need to utilize less DC link voltage. And now with these parameters, so 100 newton meters, we need like 250 amps phase. And then you see we're determining the switching states, we're getting the vector states of the voltage, sine pole voltages, sine theta and pole voltages. Here we have the pole voltage and phase current. You can see there's a slight phase shift there because we have like a 0.94 power factor with third harmonic injection. You see that third harmonic. Then we get the DC link current in. That's the combination of the AC plus the DC component. We subtract out the DC component. That allows us to get the AC component going through the capacitors. Then we use I is equal to C dV dt, calculate what the voltage ripple is, and now we have the voltage ripple for all these examples. And then at the end, I'm just multiplying the DC power in and the AC power out and the mechanical power out, and then we're calculating the efficiency again, only really including the resistive losses of the windings. And that's why I want to make a fourth part covering inverter losses, or at least an estimate of inverter losses. But yeah, I guess I'll just end it here. Thanks for sticking around if you made it through all three of these super long videos. I hope I didn't ramble too much. I think in this last one I've just been rambling the whole time. So, but yeah, thank you for watching. I hope you find this useful and informational. I don't know.